The problem statement from GATE Physics 2015 reads as follows. In the simple current source shown in the figure, Q1 and Q2 are identical transistors with current gain beta equal to 100 and VBE equal to 0.7 volts. This is the circuit diagram that has been shown to us. The power supply is 30 volts. And the question asks the current I0 in milliamperes is. This is a numerical answer type question, and once we find our answer, we have to round it off up to 2 decimal places. Before we begin the questions, let's just have a brief look into the DC analysis of BJT. So this is what, as you know, that BJT has two PN junctions. So one is the base emitter, the other is base collector. So depending on their biasing, we have obtained some operating regions. We'll be restricting our discussion just to this first region, which is the most commonly used region, in which the base emitter is forward biased and the base collector is reverse biased, and we call this region the forward active region. And this is the region that you are seeing. This is almost a flat line that you see. It's a slight slope, but we'll ignore the slope for now and we'll assume that this is a flat line. This is the region between B and C, this whole big portion that you see over here. Now so this is the region, and we notice that in this region the collector current on the y-axis, which is IC here, is independent of VCE. You see that VCE is changing, but collector current is almost constant. So which means that it can serve as a good current source. The good current source is whatever voltage you apply, the current should be constant. So it can serve as a good current source, and it only depends on IB, as we see here, right? As we increase the IB, because we know that the beta equal to IC upon IB. So this gives us IC as beta IB. So as IB increases in this direction, naturally IC should also increase according to this formula. Right, so we have established that BJT can be used as a current source. Now in our problem, we were given this as the Q1 resistor. On your screen you can see now. So this is our emitter, this is the base, and this is the collector. Now let's try to figure out what is the biasing for this Q1 transistor. So we were given that VBE equal to 0.7 volts. This means this junction is already forward biased, so we can write that base emitter is forward. Let's now talk about a voltage VCE for now, right? So if we see VCE, see VB equal to VC because they are short. So VC will also be 0.7 volts, right? So this implies that on this graph that we see over here, so we are somewhere, VC is 0.7, we are here somewhere on this line, right, on this vertical line, and B is forward biased. So effectively we are at this junction, at any one of these lines. So I'm just going to say that we are somewhere on this vertical line, right? So we are at the so to speak, we are at the junction of the saturation region and the forward active region. But it's fair, it's a fair assumption that we'll assume that we are just at the forward active region. We have just entered the forward active region. All right, so again this is the we have assumed that our Q1 transistor is in the forward active mode, and this is the schematic that we can see that this is reverse, this is forward bias, collector base is reverse biased, and we are providing. So VCB in our case will be very close to, in fact it will be exactly 0, right, because collector and base are shorted, right? So the number of electrons are ejected from the emitter, some will recombine while most will collect at the collector. That's how a BJT works, and these are the expressions that we can use to analyze our BJT in forward active mode, where the first expression that you see is nothing but the Kirchhoff's current law. I is the current going out, IB and IC are the current going in. Beta is the current gain, is defined as collector current over base current, and alpha is, which we use sometimes, defined as collector current over emitter current. Now coming back to our problem, so we were so this was the circuit diagram that given to us. Now look in this green rectangle that we have, and just focus on Q1 and Q2 transistors. Now, we were given that they were identical transistors, right? The problem stated that they were identical. What do you mean they were identical? So we can make a few comments that their doping for all the three regions, doping of let's say E1 equal to E2, whatever the doping is. Similarly for collector are the same, and similarly for the bases. And the widths of the respective regions, width of E1 equal to E2, C1 equal to C2, B1 equal to B2. That's what we mean that they are the same. And also all the other materials and all the other geometries are exactly the same. So material and geometry is the same. What this information tells us is that if we apply, by any means, if we apply the same bias to Q1 and Q2, this will result in same current in Q1 and Q2. And as a matter of fact, what happens is that we were given VBE equal to 0.7. Now note that base is the same for both. This is the base, correct? So base is the same for both, and emitter is also same for so BE. So we can write VBE1 equal to VBE2 equal to 0.7. We can say that this implies IB1 should be equal to IB2, whatever be the value, but we can comfortably say that because the transistors are identical as well as their biasing is the same. So I'm going to do that. So what I have done is that, so I have just marked two nodes VC1 and VB here, and I've also put some currents which you can see here. Now we have already obtained that IB1 equal to IB2. Now it's also given that beta1 equal to beta2, right? So this will also give us that IC1 should be equal to IC2, and IC2 is nothing but I0. Note that this is the collector current for Q2, so this is equal to I0. So this is the second expression that we have obtained, and this was our first expression, right? So what I'm going to do now is I'm going to change the color a little bit. I'm going to use the blue color now, right? So now what we'll do is that, so this was a step 1, right? Now let's do the step 2 over here. So in step 2, what I'm going to do is I'm going to do KCL at node VB. So let's just write all the incoming current. So all the incoming current is IB, and the outgoing current, look at this node, the incoming current is this IB, and there are two outgoing currents, one to the left, the other to the right. So it will be IB1 plus IB2, right? Yeah. So I'll simply write it as 2 times IB2. Why? Because IB1 equal to IB2, already obtained that. And again I can write it as IC2 over beta, because IB is equal to IC over beta, and we know that IC2 is nothing but I0, which we obtained here. So I can write it as 2 I0 over beta. Okay, so I have obtained IB as 2 I0 over beta, and let's call this as expression 3. Now what I'm going to do is step 3 is KCL at node VC1. So again, incoming current equal to outgoing current. The incoming current is nothing but capital I, and the outgoing current is nothing but IC1 plus IB. Now IC1 I know is I0, so I'll write it as I0, you see here, and IB is nothing but 2 I0 over beta. So this gives me I equal to, I'll take I0 common, 1 plus 2 over beta, and the value of beta is 100, so this will have to be 1.02 times I0. So this, let's call this expression as 4, right? So now what I'm going to do, I'm going to change the color again, and yeah, let's do now step 4, which is in green. Okay, I'm going to do step 4 now. What in step 4, I'll apply I'll apply Ohm's law. I'm going to apply the Ohm's law across 5 kilo ohms resistor. Okay, so that will be 30 minus VC1 equal to I times 5k, right? Simple. Now what is the value of VC1? Now note that VC1 is nothing but VB because this is short here. Okay, so VC1 is nothing but VB, so I can write 30 minus VB equal to, the value of I is 1.02 I naught times 5k. Now from this I can obtain I naught as 30 minus VB over 1.02 times 5k. What is the value of VB? VB is 1.7. VE is grounded. This is VE, right? This is ground. So VB is nothing but 0.7. So this will come out to 29.3 divided by 1.02 times 5k. And if we solve this, we'll get 5.75 milliamps. So we have obtained the value of I naught to be 5.75 milliamps, and we can simply put this answer here, which is we were required to find up to 2 decimal places, and we have done exactly that. The current through this transistor is dependent only on the power supply 30 volts and the bias resistor here. So that's why this value will remain constant. This value will change only when these two will change, and hence it's a good current source, right? So that's all. The answer is 5.75 milliamps. Thank you for listening.